All right, let's talk about some basic growth and decay. Um, Generally, we start with time zero, or years after 1980 or something like that. We set zero to be the beginning of the first year. That's the general process. And if you've got exponential decay, that means you're going something like this. And if you've got exponential growth, it means you're doing something like this. Right. And again, I did before zero just to show you the idea of what's going on, but usually in an applied problem, we're not talking about negative time. Um, the maximum there approaches infinity. It grows without bound, and the red exponential decay gets very, very close to zero, but never quite there. Asymptote, horizontal asymptote. And it's pretty easy to tell which is exponential decay and which is exponential growth, looking at the algebra of it. So when you've got that growth, you've got an exponential function with a positive constant times the variable. I'll call it x, even though it might be t. And when you've got exponential decay, then you've got, I'll write b just to remind you, basis change. Uh, and it's a negative value, right? Negative values really mean you're writing a fraction. So the larger b to the power kx gets, the smaller the final result. Negative exponents really mean division. So that's why you've got your growth and decay, and it's easy to recognize. Now, the issue is probably converting language to formulas. So there's generally two things where that happens. One's called half-lives. That's radioactive decay. That's the half-life story and it is exponential decay, right? You've got a certain amount of stuff, and it decays over time, and they tell you, half of it goes away every whatever 1,000 years. The other one is usually expressed as continuous growth. They usually talk about population with continuous growth. You can also talk about continuously compounded interest. It's nice when they say continuous growth because that's always going to be, or decay, right? You could be gaining or losing. Because that's always e to the power something x. I'll just like kind of put a little scribble in front of there because it's plus, it's minus, it's above one, close to one, that kind of thing. That that tells you the story there. Half-life? Oh, right. The base is 1/2. It's going to be 1/2 to, again, I'll kind of draw some scribbles and then you'll end with x depending on the story. But the idea here is that both of them are involved in exponents. Half-life is 1/2 to whatever, continuous growth is e to whatever. And remember that decay is generally about negative exponents. Well, 1/2 could really be rewritten as 2 to the negative 1. So this is really 2 to the negative scribble x, right? So I'm not actually breaking the rule when I say decay is about negative exponents. we're not actually going to write it as 2 to the power negative 1. We'll just write it as 1/2 to a positive power. Just, it simplifies matters to not have to worry about a minus sign floating around. Let me do a couple of examples. Hopefully that will help you solidify the ability to turn words into one of these two simple formats. So let's do a half-life. Half-life of, right? I'm going to make it easy. Half-life of 1,000 years. I'll make it slightly harder. 1,200, 12,000 years. Start with 100. It doesn't really matter what the units are. So I'll just say units. Make sure that when you're reading a story problem, the units don't change. If they do, make sure to convert so that they're in the same kind of unit, right? 1 kilogram goes to 500 grams, right? You better convert that 1 kilogram to 1,000 grams. Now they're comparable. Start with 100 units, and I'll just make this simple. What is a model of amount after, let's use T years. Okay. Well, let's take a look at this, right? I said half-lives mean that we want to start with 1/2, right? Half-life. So let's put that power 1/2 there. And let's think about it, right? A half-life means that after that amount of time, you'll have half as much as you started with. Well, if we start with 100 here, right, and we go to 1 half-life, if we go through 1 half-life, 100 times, well, 1/2 to the first is just 1/2. You'll have 50 left. If we had instead 2 half-lives, 1/2 squared is 1/4. 1/4 of 100 is 25, right? It just follows that 100 after 1/2 at the beginning, 50 after 1 half-life, 25 after 2 half-lives, 12.5 after 3 half-lives, and so on. But we don't want to just count in crude half-lives. They asked for a model after T years. They didn't want us to be talking in terms of half-lives. But remember, 1 half-life is 12,000 years. So why don't we just take the number of years and divide by 12,000, right? Think about it. Let's put the T in here and let's divide by 12,000. Now remember, it said after 1 half-life, you should have 50 left. That's what a half-life means. So how would we get 50 out of this whole equation? Well, we want 100 times a half. That means we want this number circled to be a 1 after 12,000 years. And that's exactly what it is, right? Divided by 12,000, the number of years. If it's 12,000 years divided by 12,000, you get a 1. And so you get 50 at T equals 12,000. 25, right? That would be 2 half-lives. Well, to have 2 half-lives, you need to be doing the 1/2 squared, so you'd need T equals 24,000, and so on, right? Making the model is not the complex part, right? You just kind of think to yourself in half-lives and then go, oh, one half-life is 12,000 years, I better divide T by 12,000. If it's some bizarre chemical compound and the half-life is in months or hours or seconds, well, adjust your time unit and divide or multiply as appropriate. You can always check yourself to make sure you have half as much after one half-life. Make sure the algebra follows from the formula. So there we go. Of course, we usually don't stop there. Usually there's questions, right? Interesting questions like, hey, what about how long? How long does it take, right? How long to get to a certain amount? So this is the same model as above. Let's not change that. How long to decay until only 37.5 units left? Now, I picked 37.5 because it's the average of 50 and 25, right? 50 plus 25 is 75. 75 divided by 2 is 37.5. I don't ever want you to say the time is the average. This is not a straight line where you can average the x coordinates and therefore average the y coordinates. This is a curvy function. For curvy functions, the middle input does not mean the middle output. The middle output does not mean the middle input. It curves. Middle matching middle is a property of linear functions only. So we have to actually work at this. But it's not that much of a big deal, right? We already have in green, circled in green, we've got the formula for how much there is left after T years. And we're being asked how long, right? How many years to decay until that amount circled in green is 37.5. So let's solve for T. Right? So here's the amount we're aiming at. And we want to know when this formula equals 37.5. There it is. I'll be a little sarcastic. All we have to do is solve for T. It's really not a small deal to solve for T because T is stuck up in an exponent. Ugh, right? Well, the nice thing about something being stuck up in an exponent is if you pull it down, to pull it down from the exponent, you can use logarithms. And that's exactly what we're going to do. We're going to use logarithms. To simplify a little bit, I'm going to divide both sides by 100 first, right? We never really needed the 100, right? That just moves the decimal over 2. So this is really going to be 0.375 after I divide by 100. Right, so we never really needed that except to realize, oh, divide on both sides. We'll have a simpler equation to deal with. Right, now the original 100 is taken care of. Logarithm of both sides. The natural logarithm of this equals the natural logarithm of the other side. Now let's put big parentheses for the natural logarithm. I'm going to write this horizontally just to help us realize that the whole thing is an exponent. and then close the big parentheses for the thing that you're taking the natural logarithm of. But remember, the whole reason we did natural logarithms was to pull an exponent down, and that's the really important rule for natural logarithms, that for any kind of logarithm that you want to do. An exponent on the inside of a natural logarithm can be rewritten as a multiple. So we can literally just rewrite that term as t over 12,000. And then all that remains is the natural logarithm of 1/2. Now, I'll trust in your algebra abilities here, right? We are trying to solve for the t, right? I hope I can trust you to, right? Here's the left side of the equation. Here's the right side of the equation. Um, I hope you'll see, right? We can multiply both sides by 12,000 and then divide both sides by the natural logarithm of 1/2. Clearly, this is now calculator work, right? Type it in very carefully, right? It is 12,000 natural log of our 0.375. And then we are dividing by the natural logarithm of 1/2. Watch out for your parentheses when you punch this into your calculator. That's the answer. Whatever messy answer that is, that's the answer. Yes, it will be somewhere between 12,000 and 24,000 years. We already knew that because, right, it has to decay. It has to be more than 1/2 life, but less than 2, because it is between 50 and 25, just not the average of those two. You'll find it's not horribly far off the middle, but it's certainly far off enough that you should never estimate with the middle. Oh, I also wanted to speak of calculators now that we've brought them up, right? You can't do this problem without using your calculator. So I really want to remind you, or maybe it's not remind, just tell you that you can certainly do this problem nearly completely on your calculator. Give me just a moment and I will show you what's going on. Right, we had, let's go back to the black ink. We had that f of t, it's the 100, right? That was the 100 units. And then it was the half-life, so it's a half to a power of. And then it was t over 12,000, because we're measuring t in units, in years, and half-lives, right? So you need 12,000 for t to get to a half-life of 1, right? Half-life of 1 would mean that it's 1/2 to the first power. So there you go, right? And if we were being asked to find t, I'll shrink this, right? What's the t when we have the 37.5 as the amount? Well, just get it in your calculator, right? You're actually just type the first function in as y1 of x, right? And then of course you type all this in. Watch out for parentheses, etc. Um, It's going to be x, of course, because that's the variable it uses. Uh, just to remind you, you want that whole thing in parentheses. You'll have that little caret to signify. I think you need a time sign over here when you're typing into the calculator. And then you'll have a graph on the calculator. You can graph it. Well, actually, don't just graph it, right? Graph the solution you're looking for, and then you can graph them both, and you can use your calculator's ability to intersect, right? It's one of the functions that you can access while you're in that graphing mode. And right, I don't know what letter it is, but I'll just say intersect. And then what you do is you literally click somewhere to the left of where you see it, right? That'll be one-ish because on your sorry, that'll be, 12, 13, 14, 15,000, something like that. And then it asks you to click on something to the right, and then you just hit enter, and right, something greater than that, and then of course it's going to be less than 24,000 because it is less than two half-lives. Then you hit enter, and it gives you the exact x value of their intersection. Um, there might be a step in there where you have to click on y1 of x as this is the first graph, and then click on y2 of x to indicate that's the second graph. So you say which two graphs you want to intersect, then you give it an interval that includes the intersection you want, and then you hit enter, and boom, you're done. I have been told that's the way I do it when I don't feel like doing logarithmic algebra. I've also been told that there's something called numerical estimation, numerically estimate, or numerical solution. There's something that says number or numerical in it. I've heard it's like an extra menu down. Something like that. I'm not quite sure. Um, you don't even need the second function. You're gonna hit that numerical solution, numerically solve idea, and I think you type in the 37.5, and it gives you the answer. Or it might be that you write down the function and you subtract 37.5, and it numerically solves the root. In other words, it numerically solves where the answer is 0, which is where the graph and the 37.5 are equal because you did the subtract in between. I invite you to take a look. I know less about that capability of the TI-84 plus CE, but I've been told it is there by some students. I like the graphical because I'm a visual thinker, and I can double check and make sure everything I've done makes sense. If I see exponential growth when it's half-lives, I know my finger slipped somewhere. Okay, so let's talk about the final thing, exponential growth. That's when the growth is, right, when it's continuous exponential growth, continuous growth or decay. Um, for that one, all you need to do is put the percentage growth or decay. Um, let me phrase this carefully. Uh, as the exponent of e. So if I had 4% continuous growth, I would write e to the point, now technically 0.04x. Now that's x would be counted in years if my 4% growth was annual. If this is bacteria growing in a petri dish and they say 4% growth per hour, then my x would be counted in hours. So remember to match up your time units. Decay, well, I mean, same thing. If you're decaying by 6%, then you would simply use E with negative 0.06x. It's as simple as that. Oh, by the way, right, there's always the, I don't know, let's call this the amount, right? If they told you that the money of $12,000 is growing at 4% continuously compounded, how much will you have after, 3.75 years, right? Oh, okay. The amount always goes in front, multiplied by that exponential term, right? If this was bacteria dying off in a petri dish at a rate of 6% per hour, hey, how much is left after 24 hours, right? And they tell you, I don't know, number of bacteria or maybe even weight. I don't really know how they give you that. I don't know enough biology. For a math story problem, I think they just give you the number. There's a million bacteria in the petri dish, but antibacterial solution has been added, and they start dying at 6% um, per hour. How many left after 1 hour? Right? You start with a million, you figure it out. All calculator work. And again, I won't display it or talk about it too much. But again, if they ask you a tougher question like when will there be 100,000 bacteria left, then you're stuck. Oh, I'm setting a million times e to the negative 0.06x. I'm setting it right equal to 100,000. And then you just go, and therefore I'm solving for the thing in the exponent. Well, see prior page about, right? So now we have a million here, but the first thing you're going to do is the trick, right? Of might as well just divide by a million, so you've got your exponential, right? Negative 0.06x, and that's just going to be 0.1, right? 100,000 out of a million is 10% or 0.1. How are you going to solve that? Use your algebraic ability to do natural logarithms. It's a little faster because natural log of e cancels out. So, but you still need your calculator because you got a natural log of a number on the right-hand side. A little easier than the page before using algebra, but you still need your calculator at the end. And if you're going to pick up your calculator and you're more comfortable with numerically solving or graphing the two and seeing where they intersect, then please pick up your calculator from the beginning and do that instead of logarithmic algebra. I kind of want you to want to do the logarithmic algebra because that means you're good at logarithmic algebra, and I'm sure that's something that's on the test also, just your ability to handle um, the algebra of logarithms. And they might do that purely on its own, although they also might stash it inside a story problem as an option, right? You can use your calculator for this. They can give you something that's all variables that you might need to know the algebra of logarithms to solve. So I do encourage you to study the algebra of logarithms. That can be a separate video.